A single spark in a server rack can escalate into a massive thermal event in seconds. When this happens, a facility manager's first defense is often pointing to a binder that says the data center was built to the latest codes. But specifying the latest standard in a contract offers no protection on its own. A code only has teeth if it is the specifically adopted edition, enforced by a project-approved design basis that forms the actual legal contract. To understand what actually governs a facility, we use this 5-tiered standards hierarchy. The bottom 2 tiers form our uncompromisable bedrock. The red layer represents local laws, the authority having jurisdiction, and the fire brigade, or DOMCAR. These dictate mandatory building permits, fire access, and water supply. Right above it are the specifically adopted codes, like NFPA or SNI, which legally mandate the design and life safety basis. The middle layers shift from life safety to commercial protection. Insurers dictate property loss and business interruption requirements, while frameworks like TIA 942 define the IT infrastructure's operational reliability. At the peak of the pyramid sits the owner's risk policy. This is where operators define their residual downtime risk and final availability targets. The hierarchy enforces one strict rule: authority governs before preference. An owner can choose to accept a commercial risk up top, but they can never waive a statutory life safety or fire access requirement at the bottom. Understanding the hierarchy is only the first step. The real challenge is proving those abstract rules actually exist in the physical data hall. This flowchart illustrates why a requirement is not closed just because it appears in a specification. It only becomes real when it is tracked through a rigorous 5-step chain of evidence. First, we isolate a specific clause and its acceptance owner. Then, that clause must generate a concrete design response, a specific calculation, drawing, or cause and effect matrix. That design then becomes a physical installed asset with a specific tag and listing. But installation is only a midpoint. It requires commissioning proof, witnessed results from site acceptance testing or integrated system testing. Finally, the system must be maintained. Step 5 ties the physical hardware to ongoing lifecycle records, standard operating procedures, and impairment logs. This matrix maps how we resolve the conflicts that inevitably arise between these different evidence sources. In the certification versus fire code row, if an IT availability objective conflicts with a smoke control shutdown requirement, life safety command strictly governs. True compliance is an unbroken chain. If any code requirement cannot be directly mapped, all the way to a field test record and an ongoing maintenance log, that facility is exposed. This 3D layout maps how our standards actually attach to the physical building. Notice how the blue IT framework and the red fire alarm and suppression codes converge on the central data hall. This cross-section highlights a massive problem inside those halls: high airflow physics. Cold aisle supply and powerful recirculation units push massive volumes of air through the server racks. That forced air pulls low-density smoke, like the kind generated by an overheating cable or a power supply fault, away from traditional ceiling spot detectors. The threat is diluted before it ever reaches the ceiling plenum detection zones. The engineered response is active aspirating smoke detection, or ASD. Instead of waiting for smoke to rise, ASD uses a mechanical aspirator to physically pull air samples directly from the forced airflow paths, such as this critical rat capillary. But you can't just install ASD piping and hope it works. This transit calculation shows the strict mathematical verification required by code. Engineers must balance pipe length, force schedule, and listed detector limits to prove that air from the furthest point reaches the sensor rapidly. Here, a pipe transit time of 29.45 seconds keeps the total transport time well under the 60-second limit required by NFPA. A software model passing the calculation is mandatory, but it's only half the requirement. The verification rule dictates that the software model must be proven by a physical, farthest point field test during commissioning. Relying on generic ceiling detection in high airflow environments invites failure. The physics of a data hall require bespoke, mathematically verified active sampling. Once that physical detection network captures a threat, we have to look at how the facility's digital brain processes the signal. This diagram shows the strict segregation required between life safety command and IT telemetry.
A single ASD detector must feed 2 completely distinct systems. The top path is command discipline. Alarm, release, evacuation, and shutdown sequences must be executed exclusively by a hardwired, listed fire alarm control panel. The bottom path is read-only awareness. The Building Management System and DCIM receive status updates, trends, and trouble tickets via Ethernet, providing situational awareness to the IT team. The control safeguard here is absolute. Commercial software platforms cannot hold any implicit life safety command authority. If a network switch fails or a technician accidentally pulls an Ethernet cable during routine maintenance, a software-based release system would be completely blinded. Hardwired panels guarantee the signal reaches the suppression system regardless of IT network status. Situational awareness gives operators the data they need to investigate. But physical life safety interventions must remain hardwired, isolated, and immune to network vulnerabilities. The IT equipment relies on a massive footprint of support infrastructure, and these mechanical and electrical zones present entirely different fire profiles. This matrix breaks down electrical hazard families. The diagnostic needs for a traditional VRLA battery room focus heavily on ventilation and hydrogen gas monitoring, which differs significantly from a modern lithium-ion energy storage system. In lithium-ion environments, clean agent suppression alone cannot solve thermal runaway or exposure cooling. These systems demand robust off-gas detection and physical containment strategies dictated by NFPA 855. Now look at the heavy utilities required to keep the facility running during a grid failure: bulk fuel, emergency generators, and suppression water supplies. Approving these suppression utilities requires verifying usable volume, hydrant flow tests, and physical interfaces for the fire brigade. The nameplate on the tank is only the starting point. The same rigor applies to smoke control. Acceptance demands physical proof of pressure differentials across doors and functional tests of firefighter manual overrides. The data center operates as a collection of distinct volatile microenvironments. Each one demands uniquely verified physics and testing protocols. When an alarm triggers at 3 a.m., the Security Operations Center is suddenly thrust into a high-pressure, chaotic environment. This interface map shows how we prevent panic by enforcing an absolute operator rule. Every system alert, alarm, or fault requires a pre-scripted response. Operators investigate, escalate, isolate, or open an impairment record. They never guess. Terminal 01 shows an early trend ASD alert, which prompts a calm investigation and a trouble ticket. Terminal 02 shows a critical fire alarm, which immediately triggers the approved cause and effect evacuation and pre-action sequences. Every action an operator takes and every response the system generates must be logged for post-incident audits in what we call the evidence vault. This timeline shows the strict chronological synchronization required to prove compliance. The timestamp of the source stimulus must align with the detector log, the FACP event, the server log, and finally the operator's authorized reset. The most advanced engineering in the world is useless if the human operational response isn't scripted, disciplined, and forensically timestamped. Even after a perfect handover, facilities degrade, standards update, and owners face constant commercial pressure to modify layouts for better uptime. This ledger of risk clearly defines the uncrossable boundaries of facility management. The green column shows residual risks an owner is permitted to accept, like downtime trade-offs. The red column shows what they cannot touch, such as disabling life safety features. When an owner does accept a residual risk, it requires a formal package: a deviation statement, documented hazard impact, compensating controls, and signed authority decisions. Any time a modification is made, whether to a physical rack or a software sequence, it must run through this Management of Change, or MOC cycle. The cycle starts with a trigger event, moves through a rigorous impact assessment and approval route, and ensures controlled implementation before ending with verification testing and evidence updates. Safety is an ongoing, mathematically verified discipline. No hardware, software, or procedural change is truly complete until the evidence index is updated, ensuring the facility remains protected from day one until decommissioning.